All right, here we are at part 2. Welcome back, my chemistry students. I hope that you're enjoying your study of calorimetry so far. We're now going to talk about a couple instruments for measuring heat transfer, and those are called calorimeters. So calorimeters are just what they say. We talked about calorimetry in the last one, being to measure heat transfer. Now, what a meter is then is an instrument used to measure. An instrument to measure. And so an instrument to measure heat transfer. And we've got a couple of them. The first one is called a coffee cup calorimeter because it's made of styrofoam cups. This is the kind you're going to use in lab tomorrow. And the whole premise of a coffee cup calorimeter is if we can confine the surroundings to an immediate area where we don't have a big loss of heat anywhere else, we can figure out how much energy the surroundings are gaining, and from that figure out how much energy the reaction is losing. So what we would have happen is we would have a reaction happen here in this calorimeter. So we have some kind of reaction. If this is an exothermic reaction, it's going to give off heat when the reaction occurs. Now, if we can contain that heat within the solution in the styrofoam cups, we can study the solution and understand how much heat was given off by the reaction. So by that giving off heat, and we can study endothermic reactions too, but we'll study that exothermic reaction if we're going to study how much energy does the water gain that's in that solution. And you can see a couple things here. There's a thermometer, a stirrer, so that we can keep that temperature constant. Tomorrow in lab, you'll use the thermometer as your stirrer. Couple different styrofoam cups that are cradled together, and we keep them together in order to insulate as much as we can. I mean, the big thing is insulation. So exothermic reaction, giving off heat, and the whole premise of constant pressure calorimetry, of coffee cup calorimetry, is that the heat that's gained or lost by the solution is going to be equal to negative of the heat lost by the reaction or gained by the reaction. So basically how the solution changes heat is going to be affected by what the reaction does. So if the solution gains heat, it was lost by the reaction. If the solution goes down in heat, it's going to have been gained by the reaction, and that way we can study it. So we know that Q of the solution is equal to specific heat of the solution times the mass of the solution times the change in temperature of the solution. And since we know that, then we could say Q of the reaction is equal to negative specific heat of the solution times mass of the solution times change in temperature of the solution. And then we can understand what we're trying to do here. So, best way to do this is to do an example. It says, in an experiment, a student added 1.01 grams of lithium bromide to 12.21 grams of water at 20.1 degrees Celsius in an insulated calorimeter. After stirring the solution for a while, the temperature of the mixture rose to 31.3 degrees Celsius. Calculate the molar heat of solution for lithium bromide. So what we want this to be in is kilojoules per mole of LIBR at the end. That would be our molar heat of solution. So here's what we're going to do. We're going to say, all right, if we know what's happening to our solution, our water, we're going to know what's happening to our lithium bromide as it's dissolving. So we're going to find the Q, we're going to find the Q of our water by taking the specific heat of water, which you can find up above or on your reference sheet, the mass of the water, and the change in temperature of the water that happened when we dissolved that lithium bromide. So The specific heat of the water is going to be 4.18 joules per gram degree Celsius. You can use the 4.184 if you'd like. The mass of the water is 12.21 grams. The change in temperature of the water is 31.3 degrees minus 20.1 degrees. And that's going to give us our change in temperature of the water. When we calculate that out, we're going to get 571.62336, significant to that third digit. And that's going to be labeled in joules. That's the energy gained by the water. Now, that's how much energy was gained by the water, lost by the lithium bromide. So now that we can say the Q of the reaction is negative 571.62336 joules. And then we're going to need to think about, we want kilojoules per mole of LIBR. Well, we dissolved 1.01 grams of LIBR. We want kilojoules per mole to get a molar heat of solution. So 1,000 joules in a kilojoule is going to get us to kilojoules. 1 mole of lithium bromide is equal to molar mass of lithium, 6.94, plus the molar mass of bromine, 79.9, 86.84 grams. That is going to get us kilojoules per mole. So we make this calculation, minus 571.62336 times 86.84 divided by 1.01 divided by 1,000, and we get negative 49.148, which to significant figures, this one was significant to 3, this has 3, this has 4, so we want 3, negative 49.1 kilojoules per mole. And that's going to be an enthalpy, because if you remember, delta H is going to be equal to Q in this case. So that's our calculation, and that's where we're going with that. The other experimental thing that we're going to do is look at a bomb calorimeter, which is a way more fun word to say. But a bomb calorimeter is just a different kind of calorimeter where we have constant volume, so it has really thick walls, and it's used for combustion reactions mostly. But the premise is the same. We're going to have a reaction happen in here, and that's going to be an exothermic reaction. That's actually going to give off a bunch of gas, and that's why we want constant volume so that we don't explode the bomb. But that's why it's called a bomb, because it could happen. We can have a big buildup of pressure. But we have that exothermic reaction, same idea, except in this case we're going to have we're going to know the heat capacity of the calorimeter itself. So we're going to take the Q of our reaction, and we're going to find that by taking the heat capacity of the calorimeter times delta T. The negative arises from the fact that the reaction is going to lose the energy that the calorimeter gains. So negative Q of the reaction equals positive Q of the calorimeter. That's why that happens. This is the heat capacity of our calorimeter. And that's going to be, again, in kilojoules per degree Celsius usually. So for every calorimeter, it tells us how much energy is required to change the temperature of that calorimeter. Everything else you can kind of see is similar. You've got a supply of oxygen there in the vessel because it is combustion. And then we're increasing the temperature of water surrounding it. There's a thermometer that's measuring temperature, and that's what's happening there. So this should actually be example problem 4 in our notes today. But it says when 2 grams of methylhydrazine, gives you the formula there, is burned in a bomb calorimeter with a heat capacity of 7.794 kilojoules per degree Celsius. So we have that heat capacity, 7.794 kilojoules for every degree Celsius change in that calorimeter. And the temperature is going to increase from 25 degrees to 32.35 degrees Celsius, which is going to give us a temperature change of 7.35 degrees Celsius. So we have a heat capacity and our change in temperature. We're going to find the Q of our reaction by taking the heat capacity of that calorimeter, 7.794 kilojoules per degree Celsius, multiplying it by 7.35 degrees Celsius, which was our temperature change when we burned that methylhydrazine. And we're going to get a value of negative, oh, and it's a negative, because of that negative up there, sorry. Negative 57.2859 kilojoules. So what that's saying is that in order to raise the temperature of that calorimeter by that 7.35 degrees, that reaction released 57 kilojoules of energy. That's total energy released by that 2 grams. So we want, again, kilojoules per mole for the reaction. So if we want to know that, we're going to take that value, negative 57.2859 kilojoules, and that's how much energy was released when we burned 2 grams of that methylhydrazine, CH6N2. We're going to add up a molar mass of that, 46.07 grams per 1 mole. And that's going to get us our kilojoules per mole. Delta H of the reaction is going to be negative 1320 kilojoules per mole when we take significant digits into account. Once we know the heat capacity of the calorimeter, we know the temperature change, we can find the Q of the reaction that happened, and then manipulate that based on how much of the stuff we burned. So a couple of different ways to look at measuring that heat transfer, both with a coffee cup calorimeter